Okay, why don't we go ahead and get started? And again, welcome to today's IWCS webinar. My name is Dave Cadu. I'm honored to be your IWCS CEO and director, and I will be your moderator for today's webinar event. A few housekeeping items for your information. As an attendee, you are part of a larger audience. So during the presentation, all participants will remain in listen-only mode. And as a reminder, this event is being recorded for rebroadcast. We encourage you to submit your written questions at any time during the presentation using the chat panel on the right of your screen. So select the chat button on your Teams screen and enter your questions. After typing your questions, make sure you hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. Our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. And today we certainly welcome Taylor Towery, cable technology mechanical design engineer at Corning Optical Communications, located in North Carolina, USA. Taylor will be presenting his paper on innovative high fiber density, low fiber count cables with two-piece armor. This presentation was presented during our conference last year as paper 9-2, if you have those references. Taylor Towery is a mechanical design engineer in the cable technology group at Corning Optical Communications. He graduated from Wentworth Institute of Technology in Boston, Massachusetts, with a bachelor's degree in mechanical engineering and a minor in manufacturing in 2016. He has worked for Corning for 3 years as a project-based engineer in global cable product development. So again, we welcome with great thanks to Taylor. And Taylor, carry on.
All righty. Well, hello there. Just wanted to introduce this topic again here of innovative high fiber density, low fiber count cables with two-piece armor. More specifically, we're looking at a newly developed armored cable design which introduces the concept of a two-piece steel tape that's bonded to the outer cable jacket. So without further ado, we'll go ahead and introduce these topics. But first, I wanted to acknowledge a brief list of individuals that really helped make this presentation possible. I'm thankful for their contributions as well as their diligent efforts. So thank you to these men and women for allowing us to present this information. So first and foremost, we want to discuss, so why would we want to improve armored cable? Well, there's several reasons here, and we're going to go into each as we proceed down the slide. So the first one would be smaller. So the three main topics here would be smaller, faster, and safer. But when you're looking at this legacy armored cable here on this left-hand image, we have a profile of our previous cable design. You'll notice that it's a single corrugated steel tape, which is wrapped longitudinally around the cable core. It's kind of this greenish blue armored tape is what you're looking at here. And so one of the disadvantages here is that this requires the use of sharp blades and multiple ripcords to access the fiber. Also, with our legacy ribbon cable, there was a release layer that was applied to the top of the armor to prevent the jacket from bonding. So this is the main reason why we needed to have these ripcords to access not only the jacket, but also to remove the armor to access the stack. So as a result, this is resulting in a larger, heavier cable, which obviously is less advantageous because we know in our installation environments, we're having less and less space. It's getting more and more crowded duct space. So we want to have a smaller cable with a higher density. So we're able to really have those connections established in smaller areas. So this leads me into the new topic here of our new armored cable design. And you'll notice on the right-hand side, this is a comparison of the new design. So what we're looking here is it's a two-piece steel tape, and it's the same blue-green color. But you'll notice instead of being one piece wrapped longitudinally now, it's two pieces that are actually bonded to the outer cable jacket. And what this allows us to do is we're really able to get 60% faster core access than our legacy armor designs. And as a result, we have a new cable that's 28% smaller and about 50% lighter compared to our legacy ribbon cable. So with the new cable, there are no ripcords due to this process. And we're going to dive into this deeper. I just wanted to do a general overview so we had some images of our legacy and our new cable. So going into the discussion of smaller. So really, again, this is touching upon size and weight reductions. So we're just going to go through a quick overview of the cable, and you'll notice there's this gray, kind of a foggy color right here that's wrapping around this diameter. That's going to be part of our water blocking elements. And inside, you'll see this colorful ribbon stack, but I'm pointing to these gray strands, if you will, that are right here. These are also water swellable yarns that are able to help our water penetration performance. We have our ribbon stack here. And so this is a multicolored combo stack design. And then we notice that we have our flattened steel wire. Now this flattened steel wire provides a lot of advantages here. Really what we're looking for is the flattened steel strength element here. It helps improve the roundness of the cable, and it offers a higher strength to critical width ratio. Essentially really what that is just a cross-sectional width as a function of tensile strength. So because we're having thinner strength members, we're able to have OD reductions in the jacket wall thickness, and hence we're able to have a lighter, smaller cable. You'll notice on this right-hand side, just put some merit behind these statements. Again, we're about 28% smaller and roughly 50% lighter. And again, like I mentioned, these gray pieces, these blue-gray, blue-green, however you see it here, is the corrugated steel armor. We have a routable foam sleeve. This is to protect the fibers and give them some sort of a cushion here. And then one of the critical features here is our tear facilitation feature. And again, we'll dive in greater detail here. I just wanted to do a broad overview, introduce the topic so we can get acclimated to the new design. So touching upon the term faster. So with this two-piece armored cable design, we have these tear facilitation features and these quicker access features. So one thing to note here again, this is just a representation of the cable to get you acclimated to the design. The jacket right here is noted. Obviously, we have our armor, which is steel tape. We have our flattened steel wire. We have our water-resistant tape that I mentioned, our routable foam sleeve, and then our multicolored combo stack design. And so really what this is, it's going to consist of 8 24 fiber ribbons and 8 12 fiber ribbons. And we're able to achieve the density with this combo stack. So this, it's tough to see. Again, we'll go in greater detail in the next slides, but this small little feature right here that my cursor is pointing to, it's just a coextruded tear facilitation feature. This is what's enabling us to have this quicker access and really expose the core in a much faster, safer way. So again, one of the big distinguishing factors here is that the armor is no longer separable from the jacket. So with the two-piece design, we want bonding between the jacket and the armor. So this forms a single composite structure. This is what is really enabling us to really innovate and develop this more modern cable. So it's, again, faster access to the actual fibers themselves. So building on this faster, I mentioned these tear facilitation features that were tough to see in the previous slide. So this shows you a better view. If you imagine this kind of a sliver or a cat's eye, if you will, this gray color, this is going to be our coextruded tear facilitation feature. So this is a separate material than our jacket material. And you'll notice that these red arrows here are pointing to these dual lobes. Now, these dual lobes is essentially providing some sort of a tactile feedback. It's a visual representation of where these features are. It helps with mid-span access, so we know where to access the cable orientation-wise on the actual circumference of the circle. So this dual jacket lobe and integral coextruded feature really provides guided, and that's the key here. Those dual lobes give you a guide so you know how and where that crack is going to propagate, if you will, in regards to the jacket opening up. So it also helps with centered mid-span for ease of access to the ribbon stack. So over here on this right-hand side, I just wanted to put some merit behind these statements. So we have done some multiple studies and established average values comparing our legacy cable to our more modern two-piece design. And with an end span access, we're averaging about 9.3 minutes to gain access. With our mid-span access, it's about 14.7 with the legacy design. So moving towards our high-density two-piece design, we've reduced that down to about 4.9 minutes and for the end span, and roughly 10.6 minutes for the mid-span. Again, these are average access times. We had multiple cable end accesses that were done by numerous technicians of varying experience. So we wanted a really broad data set to get these averages established. So we had some meritable information to speak upon. And really what this means for the cable industry is that reductions in access time really do yield faster, easier, and more efficient ribbon access during field splicing. As we know, time is money, so anytime we're able to really reduce the time to access this, it's a step in the right direction. So I wanted to compare the legacy armored cable and show you really what the differences are. This slide here illustrates some examples of what our previous design consisted of with that single steel piece that's wrapped longitudinally around the core. So with our legacy design, we had glue and multiple ripcords that were required to separate the jacket and the armor individually. We had a jacket ripcord and then we had an armor ripcord. So you needed sharp tools to access this. You needed to dig into the cable to expose these, and it could present some issues because in the real world, things aren't always going according to plan. So armor access, the ripcords, they can fail if not careful. You imagine you're pulling a strand through some mild steel, so you have issues with that being abrasive or actually tearing. So if you rip that ripcord out, no pun intended here, then it's really something that is causing an issue. So what that really means for the industry is that presents lost time, and lost time becomes frustrating during field access procedures. So if we could simplify this process, if we could get rid of these margins of error, obviously that's going to be a step in the right direction. So that's how we've proceeded to essentially accomplish that goal. And I talked about safety. Now this is a big deal here. So anytime you can improve the safety of something, it's going to be value added, right? So when we're looking for a reduction in safety hazards. So one of the main features of this modern cable design is that we're really limiting the need for sharp tools. No exposed razor blades, anything that's a real potential cut hazards that we're putting ourselves in risk, and our technicians that are really utilizing this in the field, we want to make it as safe as possible. So if we can get away from having risk, let's do it. So that's what this is really allowing us to do. So the legacy ribbon cables do require the blades, whereas the modern cable does not require the blade active fiber. So again, it eliminates that hazard, if you will. So what that means is you have this peelable composite structure. You'll notice in this right-hand image, it's essentially having gloves on. We're able to grab and pull that away to delaminate from the core itself. This, again, is safer, and it enables the jacket and the armor composite to be peeled away, which, again, minimizes any potential cut hazard because we're not utilizing these tools. This image on the left is just a quick general overview. The next slide, we're going to go into access. I just wanted to get you familiarized with the procedure of not using sharps and seeing what we were able to accomplish here. So touching upon safety, yet again, to expose the ribbon fibers here, we have a simple process. Step one over here on the left-hand side is our bladeless ribbon stack access. So we're just using traditional, nothing special here. It's the needle nose pliers that we're able to really grab a hold of that jacket and armor composite and rock it back and forth in that sweeping motion you see with these arrows representing. And that really what that's doing is that's facilitating the tear. So our tear facilitation feature is really being activated in this regard. We're pulling things away. The jacket's being separated into two pieces. It's one laminate structure, and we're able to wind this down. So really step two is really all you're allowing yourself to do is to expose enough material for your hand to grab. So there's enough real estate, if you will, to really get a good purchase on that and then start to pull away by hand. Step three, you notice, is actually doing what I just spoke of. That laminate structure is being peeled back, exposing the routable foam sleeve. And in step four, you'll notice that this routable foam sleeve, now it can be teared very easily by hand. It's not necessary to utilize a ripcord, but since we have a water soluble yarn that's in there, we double that as a ripcord. So again, it's not necessary. However, if you feel the need and you'd like to, it's there as a redundancy. But again, being pinched and pulled and teared by hand is more than adequate to access that stack. So this leads us into the next topic here of our robust composite structure. I wanted to talk about this laminate bonding I keep mentioning. I wanted to talk about the jacket and the armor and the strength elements and how they are integrated together. So like mentioned previously, glue and other adhesives were utilized in our legacy design, and this was to provide a buffer. So we did not want bonding. We wanted the jacket to feel separate from the armor itself. With this design, we've done away with the glue and the other adhesives, and it's no longer allowing that to be separate. We want them to be bonded. So this provides advantages in aerial, duct, and even direct burial applications. So one of the main features here, as you'll notice on the right, just to illustrate this again here, is this two-piece armor. It provides a true composite bond. So the flattened steel wires that were mentioned are now laminated, if you will, with the jacket as well as the armor. So when the access is initiated, everything's peeling away as one clean, consistent unit. So it's a continuous laminated structure, which has provided many advantages for us in the field. So I wanted to continue on these mechanical performance tests and just really put some merit behind these statements. And let's go into the cable robustness in regards to crush performance. So over here on the left-hand side, we have a simulation result. This is comparing bonded versus non-bonded. Again, the legacy style, which is non-bonded, to our modern style, which is bonded. So for this example, we didn't have any internal components like the core, any of the routable sleeves or anything. We didn't want anything to contribute to the data. We wanted to compare apples to apples and just see what was the deflection in relation to force and how was this advantageous. So again, the non-bonded, you see it's not composite, and the bonded is composite. So the bonded really helps us with crush performance. So if you'll notice on the right-hand side, we have this graph here. On the x-axis, we're increasing our crush force. On our y-axis, we're increasing the deflection, or the displacement, if you will. So the deflection of the cable as crush force increases compared to non-bonded. Now, if you look at this trend line, we have this blue line. Now, that's representing the displacement in relation to force with our non-bonded. The orange line trend line is representing our displacement as a function of deflection with bonded. And you can see that we have about a 30% performance increase compared to the equivalent non-bonded testing. And again, this image is just really illustrating what happens with the cable when we do put compressive loading on it and how things move around. So as you can see, there's a clear advantage here having the two laminated together as one system. Moving forward to peel force as a function of armor overlap location. So I wanted to address this again here. So we're pointing out these tear facilitation features, and we have our armor overlap on this right-hand side. You'll notice there's an underlap and there's an overlap. We're more concerned with this overlap. So really what this graph in the middle is showing, it's peel force plotted over radially increasing armor overlap distances from this feature. Really, that's just a mouthful for saying that as we indicate or index rather this overlap away counterclockwise from this tear facilitation feature, peel force goes up. As we indicate or index this overlap towards this tear facilitation feature, peel force goes down. So since we have defined portions of armor bonding to the jacket, the index past these axis features, it really allows us to gain control of peel force. So all of these samples had passed not only mechanical testing, but mechanical plus testing, which we'll dive into later on here. But as a result, like I mentioned previously, this peel force can be fine-tuned for ease of access. So one question that may arise is like, well, why would you not want this to be as simple as possible to open? And the main reason is we wanted to establish a peel force that we feel that our technicians have been acclimated to. They have some sort of an intuition of how much force it takes to open these. We didn't want them just tearing them apart, and we didn't want them to really injure themselves if it was too challenging to rip apart and make things, unnecessarily forceful, if you will. So we decided that because we passed the mechanical plus testing with our different indexing, we decided that let's go ahead and make it similar to what they've seen in the past. Like I said, give them some sort of intuitive approach. And so we decided to tune this, if you will, as a similar force required as our legacy ripcords. This is going to be a quick slide here moving forward. It's just to showcase the ICEA 640 and the GR20 spec. Wanted to touch upon our industry standard. As I'm aware, I'm sure we're all familiar with these samples and these testings. We have showcased that everything has been passing to the industry standard. So that's wonderful news. But we're going to go ahead and take that a bit farther and see if we can dive into this a little bit more extreme. So that leads us to our first test, and this is going to be twist testing. So really what this is intended to do is to determine the effects of dynamic twisting with and without tension. So the standard twist test is going to be 10 cycles of 180-degree turns. So essentially that cable is going to be rotated 180 degrees, reverse back to neutral, go counterclockwise 180 degrees, reverse back to neutral, and go through 10 cycles and inspect. Is the jacket opening up? Are there any signs of any stresses that are being introduced? Is there any permanent deformation? What are we seeing here? And standard twist passes flying colors. So we decided let's go ahead and take it a step further. Let's go with twist plus. And really that enabled us to go 4 complete 360 degrees clockwise rotations, reverse it to neutral, and then reverse back counterclockwise 360 degrees, 4 complete turns in that aspect, and reverse back to neutral. And this is awesome because with the new armored cable, there's no jacket openings. And this is including down to the tear facilitation features. There's no signs of delamination, no signs of any sort of opening. where leak paths could be presented, and everything has been passing with flying colors, for lack of a better expression. I mean, this is awesome news in regards to mechanical testing. So let's continue on. Going into flex testing. So again, we have our standard flex testing, which is using 10 times the cable diameter. You'll notice in this lower image, we have a mandrel radius right here, and obviously an inverse mandrel radius on the other side. So for standard testing, we're going to go 25 cycles, essentially traversing back and forth through 25 cycles of flexing, and examine. Do we have any signs of stress, strain, permanent deformation, jacket openings, anything that's a red flag to us that is showing us failures are present? The answer is no. So again, as always, let's go ahead and test it some more. Let's see if we can get it to fail. So we went through plus testing. Now, flex plus testing is a little bit more stringent. So we're using about half the size of the mandrel radius here. So we're 5 times the cable diameter. And again, the same 25 cycles of flexing around a smaller bend radius, which you imagine would introduce much more stress and strain. And there has been no jacket openings. And again, I can't stress this enough, and that's including at the tear facilitation features. This is something that you would imagine would be a weak spot, and it's not. I mean, this is able to handle this robustness very well. So we're proud of that, and we just wanted to illustrate that and communicate the message across. Going into crush testing here. So again, our standard crush test is going to apply 220 newtons per centimeter of force. You'll notice on this left-hand image, this is a compressive load that's being placed onto the cable to essentially see where's the stress distributions, where's the strain percentages established, and we really wanted to see how is that affecting the cable. Looking for attenuation results, looking for breaks, looking for, like, again, permanent deformations, and I had no issues with that. So it passed very well. So let's go ahead and take a step further. We went and doubled that. We went to 440 newton centimeter of force. And this image here on the right, this is just a simple model of a finite element analysis. This is going to show you your stress concentrations, the distribution of this load, and more specifically a compressive load, to utilize, how the fibers are being interacted with, and is this causing any detrimental effects? And the answer is no. So the reason being is there's no jacket openings, and there's no real issue in that regard. So that's wonderful news. Again, I can't stress this enough. Even at the tear facilitation features, there's no signs of deformation, failure, anything that would present an issue or introduce a red flag of something that may be unfavorable, to say the least. So this leads us into the next topic here, and this is perhaps my personal favorite. It's the most intense test that we seem to be doing to these cables here. And really what this is, it's a torture test. And really this is just designed to exceed the minimum bend radius that's spec'd over a mandrel. That's less than half the size that's defined on Corning's mechanical specification sheet. You'll notice right here, we're using a 9-inch radius as our spec for the minimum bend radius installation. Well, what we're doing here is we're going down to a 4-inch diameter mandrel. We're, more than half the size of that reduction. So we're seeing, you would imagine there'd be higher stresses involved in that, and there are. However, these longitudinal and circumferential stress that's being applied, it's because it's being pulled around a mandrel that's 4 inches in diameter, like I mentioned, that's under tension. So we're utilizing about 300-pound force of tension. This is then taken up on a reel, and then we're analyzing the results. And again, to say the testament to the robustness of this cable, even after going through this, there's no fiber breaks, nor jacket openings. And we understand that accidents happen. There's unforeseen circumstances that befall us all. We have oops moments, if you will. So we wanted to kind of really stress this cable, figure out what happens when things don't go according to plan. Does it fail? Is it able to respond well? How robust is this? So let's continue to take it further. And really, again, we've had adequate attenuation performance. Then even with these mistakes that we were trying to simulate, there's been no issue with cable robustness. So again, a testament to the stoutness of this cable. It really showcases the ability to go and endure challenge, stress, strain, and really respond well in these environments. As we know, in the technicians in the field, there's not really a light duty application. Things are getting pulled, things are getting moved and forced into areas, and there's going to be stresses that are introduced. We wanted to understand, can we survive that? And the answer is yes. So I just wanted to go through a brief conclusion, just to reiterate what we had discussed here. So Corning has a high fiber density, Corning's high fiber, I apologize. High fiber density, low fiber count. That was a mouthful for me. Armored cable. It truly represents an innovative breakthrough in the outside plant cable technology. So really what this means for the industry is it provides long-term reliability, whether that be aerial, duct, or even direct burial applications where you're seeing the most conditions of weather that really affect the cable here. So to review again, these tear facilitation features that really reduce the access time. It limits the overall risk of inadvertent fiber damage because it reduces the need for sharps to access the cable. We're able to just use simple hand tools like needle nose pliers and some elbow grease to really get in there, and it's been very effective. So in conclusion, like I mentioned, the compact design, the enhanced protective foam, and two-piece bonded armor is really ensuring that the ribbon stack and the cable perform as one continual unit. And this is reaping the benefits and the reason that we're innovating and introducing this new cable to replace our legacy design. So at this time, I'd like to thank you all for your time. If there's any questions that may arise, if you have any concerns, if there's anything that I can help, hopefully maybe shed some light on some things, I am all ears. So let me know if you have anything. Thank you.
Taylor, thank you so much for this excellent presentation. This is an outstanding example of the quality and tremendous technology innovation that is presented through IWCS year in and year out. So we thank you immensely for being part of this today. I remind everyone that if you have any questions for Taylor, to please enter them in the chat, and we will ask them to Taylor as time permits for the next few minutes. Taylor, is this cable available for purchase now, or is it still in development?
No, this is available for purchase in multiple fiber counts. We have them available and ready to go on the market.
That's awesome. Okay, great. There does not appear to be any longitudinal water blocking protection under the jacket and over the armor and flat steel wire. Is that correct, or is the design intentional?
The design has been intentional, so all the water blocking or water swell tape is in the critical areas, obviously inside of that two-piece armor. We have that water swellable tape, if you will, and then again, a layer below that, which is a built-in redundancy, but still gives you an insurance policy for the water swellable yarns that if the water does penetrate, it has a backup plan. So that is designed intentionally. There was unnecessary for us to have that with water penetration testing and results.
Excellent. Okay. Can this two-piece armor design be used for stranded loose tube cable?
Potentially, yes. Theoretically, yes. We have not experimented in that regard, so it's kind of a loaded question for us. But intuitively speaking, I would say yes. There is the capability of applying this technology to that design. Yes.
All right. Excellent. Okay. Any more questions? I don't see any more questions in the chat. So we'll keep an eye out just as we close our remarks this morning, but here's one. What's the minimum cable diameter required?
I would say 30x, I believe. Sorry for the hesitation. I had to just go through my mind and pull it out of there.
Mm-hmm. Okay. All right. Well, let me go ahead and then do a quick wrap up here. So let's see here. Where am I? I'm sorry. Somehow the PowerPoint got lost here. Just bear with me. Oop, that's not it. Do we see any more questions? Oop. While I'm trying to get back to the actual PowerPoint slide that we were using, I do have some contact points here that I want to share with you. Just again, bear with me for a quick second here.
Dave, it's pulled up on the screen now.
Is it?
Yes.
Excellent. Okay, I'm not sure why. Okay, anyway, note the contact points. Here we go. Have you taken, I see what you're doing. So is this your shared screen?
Yes.
Okay, yeah, I've got the PowerPoint up here, but okay, very good. Anyways, sorry about the confusion, but again, please note the contact points that are being shown here for Taylor. Should you wish to contact him with any questions or comments. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct technical paper webinars and also some sponsored company events several times each month. Our next scheduled technical paper presentation webinar will be on Friday, November 18th, Eastern USA time. That's because our 2022 conference is rapidly approaching. Each of you will be receiving an announcement for the event. Please feel free to share our announcements with your colleagues so that they can join in and register as well. Let me check any last minute questions. I do see a couple have come in after we started wrapping up here. Any special jacket material required or normal high density polyethylene material?
There's no special material as far as the jacketing. I mean, it's our just industry standards. There's no custom proprietary recipe if that's what you're after.
Okay. And how is the jacket removed for mid-span splicing?
We're utilizing the fast access or the tear facilitation features, essentially where it can be separated at those nubs, if you will, or those bumps on the cable. It's basically pulled apart from that mid-span access without the use of a ripcord.
Okay. All right. With that, before we can, it's important before we close out to recognize and thank our IWCS partner sponsors who contribute greatly to the success of IWCS and the Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you. Becky, I don't see here.
Yes, I'm sorry, Dave. I'm having trouble with this slide. The logos are not appearing.
Okay. Let me try and bring this up again. I'm not sure why we're having these difficulties today, but just bear with me for a second because I do want to bring these up. Okay, very good. I found it here. So let me share my screen, Becky.
Thank you, Dave.
And I'll bring that up. Again, we apologize for the slight delay here, but there we go. Okay. So again, these companies have been extremely generous with their contributions, not only financially, but also the technical innovation contributions to IWCS. You see Corning here through Taylor have also supported IWCS in a tremendous way. Again, thank you to these leading suppliers in our industry for your support. With great excitement, for over 70 years, we've been producing the IWCS Cable and Connectivity Industry Forum. We are the recognized leader showcasing new technologies and cable and connectivity products, processes, and applications. Our next 71st annual Cable and Connectivity Industry Forum is taking place live Monday through Thursday, October 10th through 13th at the Rhode Island Convention Center in Providence, Rhode Island. The registration and hotel reservation links, all of that can be found on our IWCS.org website. We hope that you're making plans to attend this live event so we can all be back together again after several years and hear some incredible new technologies and industry activities within the forum. So please watch your inbox, social media, and our website to learn more as additional information becomes available. But as of today, you can see the program, you can see the registration links to the conference, as well as the hotel reservations at the Omni Hotel in Providence. So thank you for your participation today. We hope you have a great weekend, and take care. Be safe.